Hi, everyone. Is the voice good? Excellent. So thank you so much for coming to my talk. So this talk is about causal inference. So of course, we are all aware of the amount of tremendous success machine learning has had. And this goes beyond the traditional applications of machine learning to actually emerging areas. This morning, I actually Ubered to this venue, and these are examples of what now we are capable to do using machine learning techniques. And this is very much aided by the fact that there is basically prevalence of data, and we can collect data and process it at capacity which was not feasible even a decade or two ago. And of course, this allows us to do lots of cool applications, from automated decision systems to everything else you're using in your daily life. But the question that we want to ask here is that, is there an AI revolution? And are we there? Have we basically achieved what we needed to have? So I want to just draw your attention that there are things that we can do very much better than what we could achieve just a decade ago. For instance, deep learning is this black box that has allowed us to do amazing things to describe, to manage to work with data. Yet we have very little understanding of often what are the generating mechanisms. You can use these deep networks to, for instance, do supervised learning, decide if this is a cat or a dog, but you don't understand what is the features that make something a cat or a dog. So this is what still remains very much open. And I want to draw your attention to the fact that, sure, there has been certain amount of revolution, especially in this space of doing supervised learning. Think about applications of deep learning, but it's just a part of what, in general, we think machine learning is. And I would go beyond that and venture that artificial intelligence needs way more than that. And specifically, what we want to know is that we want to have understanding of these generating mechanisms that happen. In complex systems of many variables, we can think about rules and say like physical rules or dynamics that are unknown and are governing these complex systems. We need actually some sort of model-free, data-driven approaches that would allow us to learn the behavior of these systems and actually do further than that. And we would like to eventually control them and interact with them. So you might ask, is this all new? Is this something that we have just started doing? And I would actually say that, this complex systems with interacting parts of many, with many interacting parts is not something novel. It has always been there in social and natural sciences, as well as in econometrics and, finance. These were things that we have always been interested in. And understanding these interactions, and I mean beyond just something is correlated with another phenomena, is of fundamental interest to us. And this is precisely what the topic of my talk is. So I want to say that understanding these things, which is similar to how humans interact with their environment, requires this understanding of causation. And specifically, I want to talk about these notions of statistical causations or directional influences, right? So the classic example of this that appeared is in econometrics by Nobel laureate Clive Granger, for instance. But also it has increasingly become over time important in biology. We all care about, is a certain, say, drug or a vaccine efficient, right? So these are examples of, you want to understand causality again in these systems, right? But what is new is, I want to say that, we are going beyond, let's say, is A influencing B. We want to understand causation in these complex networks because the systems are getting more and more complex, right? So what is the goal? So to try to mathematically think about that, is the idea is that we have some network, and in this network we have some vertices. These vertices could be either random variable or their processes, and we want to understand the direction of influence. So the goal is learning not just links, but directed links in this graph. And the hope is that, these directed links are somehow capturing these directional influences or statistical causation. And we might be in a setting that you observe all these basically vertices, or you might have some latent ones, right? So you cannot observe everything. So there is two ways to approach this problem. One is so-called passive, the other one is active learning. In the passive setting, you just have observations. In the active setting, you can actually intervene in the system and then try to understand things. So this talk is for the most part talking about the passive setting. So I want to basically concentrate on that first. Where do these things happen naturally is, of course, financial networks, right? So you might want to understand how is like certain classes of stocks influencing the other ones. This could allow a hedge fund, for instance, to decide their strategies, how to invest in various stocks. And here, if the market is so big, and let's assume it's not China, right, the government cannot just intervene in the system and things are happening in a certain way. You merely have observations. Other examples on in neuroscience, we know that neurons naturally communicate with each other using this basically spike trains, which are these time series, and you cannot just intervene in the system. You can observe behavior, or you can do measurements from regions of brain, and then you want to understand what region, for instance, is influencing another one, and so on, right? So we want to talk about causality. Everybody in this room understands correlation. In our first statistic course, we know how to measure correlation, but how do you measure causality? So the most, in a sense, well-known definition of causality, at least in the time series, comes from Clive Granger, and this is this predictive view of the causation. So basically, I'm just paraphrasing this because I think the sentence is a bit convoluted, but you say that a process X is causing Y if you could better predict the future of Y knowing past of X. So this is a view that Granger had in '69. Around the same time, Rubin in Harvard had a very interesting other view, and he says that, we consider that causation between X and Y is if we change a variable X, will it result in some different outcome for Y? And both of these measures, if you think about it, are saying the same thing in a sense. A change in X has to translate in Y, otherwise knowing past of X can't be useful for you to predict future of Y. So they are in that sense similar. But also they require rich observation. So X has to vary enough, or you have to intervene, change X, such that you can indeed, have this opportunity to see that it has an influence on Y. But also you need good statistical tests and measures to be able to measure this change in Y. So they all require, in a certain sense, the same stuff. So what is hindering this? So when you talk about this rich observations, you don't always have rich observation. Hence, in language of causality or in philosophy, this creates this problem of so-called counterfactuals, right? You observe only a subset of the universe and you want to make comments about what is there in the big view of things. And in terms of whether or not you have actually tests that you can detect this becomes so-called problem of identification. Can you identify the causal effect, right? So, in a sense, in the most basic setting, you can assume, let's say we have rich observation, can I still do identification, right? And I'm going to, in this talk, assume that you always have infinite samples. So your problem is not that you cannot learn the distributions, but it's actually a challenge. So in reality, that also is the statistical challenge that we're going to have, right? So let's go back to this thing and let's revisit what Granger says. So Granger has this idea, which looks very nice. It's a predictive framework, but his formulation of the problem actually was merely for linear systems. So even though this description is general, the formulation doesn't go beyond linear systems. Also, the problem with, say, Rubin's framework is that it's pairwise, that it's not natural for the network setting, right? So both models have this, of course, again, issue that they're plagued by the counterfactual, and there might not be robust to confounders. You need causal sufficiency. You need to measure everything to be able to actually understand causation here. So what's going on in the landscape? I want to say that, we have some pairwise measures for causality, like the examples I gave you. People have done things like randomized trials, which is a form of intervention. We know how to do some of these things. In statistics, you might have heard of concepts such as instrumental variables that sometimes help you deal with these confounders and so on. But extension to networks was not there for a long time. We didn't know what to do beyond linear models. And again, this is the issue of confounders or latent influences. There is also the notion of statistical sample complexities, whether or not you have enough samples, what can you say? And of course, there is computational complexity, right? So even if you know what you have to do, can you do it in an effective way, right? Efficient way. So This Granger's formulation, as I was telling you, one has to have a little bit of formula, sorry about that, in a talk. So what he does is that he considers two predictors. So one of these predictors in this linear, basically autoregressive model, he predicts y at time t, and he has access to past of y, let's say everything else in the network, you call it z, as well as past of x. The other predictor does not have access to x. And you have some erroring model, these e's, and if somehow there's a reduction in your error, let's say one measure is you look at the variance of the error, you can have other metrics. If there is a basically reduction in the error, then you can say that, okay, x is helping me predict future of y, hence it's causal, right? As I told you, this formulation is linear and actually does not work for many interesting modalities. When I gave you the example about the neural spike trains, this would not work in that setting because you have so-called point processes where the information is at the time of the spiking, not at this regular interval. So you cannot even use this formulation here, even if life was linear. So, of course, point processes are super important. Almost everything which is interesting and you're interested in is a point process. So, in a sense, this is not applicable to any of the interesting things we want to do these days. So, what can we do? So, one thing that we have done in recent years in my chair is that noting that what Granger is talking about is fundamentally a sequential prediction. You don't need to do linear sequential prediction. There is a more general way you can think about it. So you can think about that you have a predictor that actually this notation, if you have not seen it, it just means past of y up to this time. So it's the whole indices. So you can have predictors that use past of y as well as past of x versus one that merely uses past of basically y. And then, these predictors allow you to predict an outcome. Once the outcome is revealed, you incur a loss. There's a loss function. It could be anything that you're interested in. And you can talk about this notion of regret of these two predictors. So you want to see if I use the one that has access to x, do I do better in predicting y or not, right? And in this sequential prediction framework, for instance, you can use various, again, choices. Like if you use something called logarithmic loss, you can show that the optimal predictor here is so-called beliefs or conditional probabilities. That's what you should use. And you end up getting some object which is of this form, right? So this, if you look at this, it's basically is predicting it's a soft predictor for the value of y at current time given all the information you have versus one that throws away x. And this thing actually has a name. So it's called a directed information. It has been shown in information theory to have some value in certain problems, like, say, gambling with side information and so on. But it has this nice property that now allows us to generalize this notion of Granger causality. And then we can define a notion of causation in the graph when I have time series. So I can draw an arrow from one process to another one if this value of directed information causally conditioned on past of everybody else in the network is a positive value instead of being 0. So this allows us to learn this so-called directed information graphs, and it's nice because I want to tell you that it brings two things. So it brings this information theoretic viewpoint, which comes from Claude Shannon, which was, working on problems in communication theory, but using information theory. Around the same time, Clive Granger was working on econometrics problems. And, there is this view that suddenly these two things, in a sense, meet in this space, right? There is also another view of causality, which is very predominant. It comes mostly from the computer science view. And this goes to Judea Pearl, who's a Turing Award winner. And what he does is he has these so-called directed cycles, acyclic graphs or DAGs, and then he defines a notion of causation, which is related to these Bayesian networks. If you haven't seen it, you have a basically factorization of the joint probability in a sense that each variable has a set of parents in this graph, and I can draw an arrow from all the parents that are appearing in this factorization of the joint probability, and this indeed is a generalization of this Rubin's view that I was telling you came from statistics, right? So what is nice is that if you can also use this to again describe this time series, but it's not nice to use this approach to see time series because you have to unravel it for every time instance. So as your length of observation grows, this graph just explodes, right? Which is not nice for visualization. And But what is nice is that Pearl's work was, in a sense, generalizing what Don Rubin was doing. So this was where statistics and computer science were kind of, in a sense, merging these views of causation. So what I want to say is that when your observations are indeed time series, what is beautiful is that you could have a unique factorization here. So I can also define this thing, this graph that, again, I look at processes and I see which other processes are its parents and influencing it. This is the viewpoint that Pearl is taking. But also I was telling you the other viewpoint, which was drawing an edge when you were looking at this value of this directed information, right? So it was another way to learn the graph. And what is nice is that you would learn exactly the same graph if you use these viewpoints. So why is this nice? Because it actually allows you now to merge a bunch of things. So Cloud Shannon's, this information theoretic viewpoint that we took, generalizes what was done by Clive Granger in time series. On the other hand, I told you that Judea Pearl was, by introducing these Bayesian networks, he generalized what Don Rubin was doing. And these directed information graphs merge all these viewpoints when you have time series, right? And they absolutely make no assumptions about the dynamics. They just work with the joint, right? They are applicable to any statistical model, and they basically are not tied to particular statistical tests, and they basically are suitable for visualization of time series, right? So this is what makes them very nice. What is not so nice about them is they're very complex to learn. Because if you want to do this calculation, when you talk about like conditioning on everybody else on the network, and if your network has many processes, you need to estimate high-dimensional statistics. And I don't know how many of you guys are statisticians, but as soon as you hear the word high-dimensional, you should start shivering, right? Because it's not so nice, right? So, of course, we can apply this to certain problems still, despite its complexity. So I have worked with colleagues at University of Chicago and Stanford, and we have applied it to understand, certain patterns of neural spike trends for a monkey, a primate that is moving his hand. And it's very nice because the directions you cover for the causality agrees with other modalities they have in this problem. So you see that actually you're learning the correct stuff, right? Also, we have applied it to analyze, say, Twitter network. I mean, I have looked at, how can you learn, for instance, if you are following versus news sources, how can from a tweeting activity you can learn which news sources are influencing you? And I think in this day and age of everybody cares about the bots and of course fake information, you can imagine how important it is to actually understand what are the patterns of influence that appears in networks, right? So I just want to quickly go through this. So one issue that I told you is that this is all nice and dandy, but the problem is the complexity is still nasty. So why is it so nasty? Because these are very general models. In reality, you often know something more about your model class, right? You don't need to just merely work with the joints. And if you have any side information about your model class, like every good statistician, you can actually use that to your benefit. For instance, one thing that we have studied is this so-called multivariate Hawkes processes. So these are processes that go back to 70s. Again, everything I do goes back to 70s, the origin of it for some reason. And I like the fashion of 70s as well anyway, so on a side note. So in the 70s, they were using it to understand how seismic activity in one region influences the other ones and so on. And the idea here is that, you have these processes where spiking in one increases the likelihood of spiking in another one. You can think that this is very useful, right? Think about, say, emotions. So your friends' emotions around you is going to influence you, right? If they're purchasing certain products and it becomes a trend, you're also more likely to buy this. So you can imagine these are very useful things to look at. And people have looked at actually and understood that these things in various applications actually capture naturally some notion of causation, right? And what we did in this space is that, and I don't want to go too much to the details of it, so let me skip a bit of the math, but what we can show is that, in these problems, learning some feature, which is some kernel matrix of these guys, is exactly equivalent to learning what I was talking to you about, is this directed information, right? So it suffices, instead of estimating that high dimensional joint just to estimate some matrix, which is much easier to do fundamentally, right? So it basically allows you to learn causation. And once we do these things, then, we can go beyond what was possible. In the interest of time, I want to go a bit quickly on this. And for instance, do problems that are much, much harder. So one data set we looked at is this so-called meme tracker. So what is this meme tracker? It's a data set that looks at how you create hyperlinks, right? So when you go to a certain website, how likely are you to go visit another website? And if you look at this pattern, maybe you can actually learn something about the structure of these networks, right? And indeed, this is what happens. So here, this is a much bigger network, but for visualization, I'm showing it for 60 processes. 60 websites, and you see that something interesting happens. If you look at this hyperlinking, you see these directed edges that you're learning, and there is a clustering effect that comes here. So certain websites like Amazon, Yelp, Craigslist are in this class of basically merchandising and reviewing websites. Other ones end up being news organizations, like say Huffington Post or Spiegel and so on. Yet there is another class, which is this other subgraph, that is these websites that actually write articles on different topics. Let's say it's health, beauty, lifestyle, and sometimes they also contain commercials for various products. So it's not surprising in such a website, you might then send someone to Amazon to go buy it, right? Also, you might want to talk about a study in health that appeared in Spiegel or CNN that says if you buy this nonsense cream, you're gonna, stay 20-year-old for the rest of your life, right? So, so this is basically this behavior. What is beautiful though is that you have such a different behavior in the network. So what I want to say, understanding these directional influences or causation gives you something more than of course here it gives you what is the type of these things, it gives you something about its generating mechanisms, but also for free gives you clustering. So even though I had no idea what are the clusters in the data, we just did it, and it naturally gives you this idea of how interactions help. And indeed this study was something that was funded for me in US by Department of Defense. And they claim they're interested in understanding the basically behavior of various environmentalist activist group. I don't believe that, right? But you can see that it allows you to monitor behavior, right? So who is interacting with whom. It could actually give you a lot of information for various entities that you might be interesting to understand their behavior, right? So all of this becomes feasible because we are using the fact that we now know how to learn directional influences better than before, but also this would not have been feasible if I was merely using what I told you earlier. We had to use some assumption about this model class, namely these Hawkes processes, to be able to run these simulations. And in big networks, you really need to use some clever ideas to be able to harness this and basically be able to capture the causation as well as handle the complexity. So the question is this. So I talked about this network causal inference. Are we there yet? Have we solved everything? And I want to say no, we are far from it. And some of you guys, you're young people in this room, and I think this is going to be an area that if you want to work in ML, to me, this is where you should be working, not on deep learning. These are solved and they're just going to be applications, right? This is where true research lies, you would have careers for another 50 years, I would say. So what's going on is that we know a little bit about identifiability. So if there are no latent nodes, we actually know something in this passive learning. When you have mere observations, let's say for time series, you exactly know what is identifiable or what is not identifiable. When you have random variables as your observations instead of processes, it's a little bit less known. You learn up to something called the Markov equivalence class. In terms of active learning, when you can do interventions, right? This is, let's say you're organizing drug trials, right? These type of applications when you need to do active learning. So some information, at least to some level, is understood about when you do one-shot interventions. But actually, adaptive learning, where you do intervention, you look at what you learned and you adaptively design your next step, is very much an open area, right? So you can think about, if you guys know about concepts such as bandits, it's related to bandits exploration versus exploitation and so on, right? So, you know, some basics are developed here, but a lot is unknown, right? So if you have latent stuff, it's a complete other ball game, right? So when you have basically this passive learning, some scenarios, again, you can handle it if you have time series or you have random variables, but these are very, very specific cases. Pretty much the problem stays open. And when you want to do active learning, an interventional setting, in a setting where you had latent variables, pretty much nothing is known. Also, in terms of statistical consideration, I completely ignored it. It just assumes you have enough samples. If you don't have enough samples, even the ones that I claim are solved are not really solved, right? So you don't know what to do if you, I mean, what amount of confidence, you know, you can even describe a causal relationship. It's very different than classical statistical problems when you can talk about, say, confidence intervals and so on. We don't even know how to describe our confidence in these causal models, right? And of course, the efficient algorithms for computation harnessing this computational complexity very much remains open. So I want to just end this talk on this note, that the holy grail of causality right now is this so-called causal sufficiency, which is when you don't have enough samples, as well as you don't see, you cannot observe everything, you don't observe the whole universe. And I hope you realize that this is almost always the case. We continuously make claims when we don't know if we have observed everything. We know all the players that are involved in a network. And this is where I believe that, you know, the next decade is going to be focused on. That's where, you know, all the interesting things would happen. And fundamentally, I want to just, you know, end this thing with this quote, which is very interesting to me. So basically, this is by very high profile, I would say, finance and econ gurus. This is Andrew Lowe's group, if you guys have heard of him, like is one of the top, I would say, finance econ guys at MIT. And he has this really nice work. And also, of course, Robert Merton is a Nobel laureate. So what they're talking about is that, you know, they basically say that if we want to have any policy effect, we need to understand these so-called destructive feedback loops in complex systems. Think about financial systems and so on. And you can only do that if you understand what's going on in the system. You cannot do it with black box models. What we need is these models that are explanatory and, you know, give you this causal information. Otherwise, you cannot understand these networks, you cannot control them, and you cannot have effective policies. So I want to end it on this basically note and take your questions. Thank you so much.